What happens to our understanding of the cosmos if gravity's laws are dictated strictly by the shape of the universe itself? Galaxies currently present an accounting crisis. They spin far too fast for the amount of visible matter we can detect. By standard physical laws, they should tear themselves apart. Workarounds where this missing gravity have dominated the field for decades. We search for invisible dark matter. We draft modified Newtonian dynamics, MOND. We propose hypothetical superfluid dark matter. These legacy models share a distinct methodological flaw, a reliance on empirical interpolation functions. They depend on tunable mathematical dials. This creates a post hoc trap. When the theoretical math fails to match the actual data coming in from the telescopes, physicists can easily invent a new parameter to force a fit. They tweak the dial until the line hits the dots. Turning a dial until the math works might describe the observation, but it obscures the physical mechanics. It results in a highly educated guess. Validating the true mechanics of the cosmos requires a rigid framework with zero free parameters, one that predicts the exact results before a telescope is ever turned on. The integrated toroidal centropic model, or ITSM, defines the vacuum of space as a pressurized superfluid plenum, a continuous liquid cosmos. In this environment, a massive localized object like a galaxy acts as a macroscopic stir. It physically displaces the superfluid vacuum as it moves. Normal Newtonian physics assumes that physical drag operates uniformly, with kinetic energy dissipating outward into all three spatial dimensions. The ITSM universe possesses a toroidal geometry, dictating different rules for drag. Because the manifold wraps back on itself, it creates a closed loop. This ensures fluid dissipation along the forward path is strictly suppressed. One dimension of drag is effectively deleted. The global geometry of the cosmos itself removes a full dimension of physical resistance for any moving object within it. If that forward dimension of kinetic energy is completely blocked by the universe's shape, the force must find another path. The active drag is forced into a two-dimensional transverse shear plane. We calculate this interaction using a covariant trace ratio. We divide those two active shear dimensions by the three-dimensional bulk volume, exactly 2/3. This topographical map illustrates the physical result. The sharp blue peak rising behind the node is an acoustic metric wake. This superfluid distortion creates the drag that mimics the gravitational signature of dark matter. The fraction 2/3 is a geometric necessity. It is the literal dimensional shadow cast by a three-dimensional object moving through a toroidal universe. This differentiates the ITSM from models like MOND or Superfluid Dark Matter, which rely on adjusting coefficients to match galactic rotation speeds. In this plot of 175 spark galaxies, the solid red prediction line hits the mark because that 2/3 fraction is a strict topological invariant. It is never adjusted or optimized to fit the residuals. This ratio is also shape-independent. Whether the mass is a sphere, a flat disk, or an irregular cluster, it generates an identical 2/3 fractional shadow. Because this interaction is structurally locked by the manifold, the model cannot be tuned, bent, or forced. There are absolutely no empirical dials. There is no artificial curve fitting, just pure universe geometry locking the entire framework permanently into place. Identifying the precise shape casting these cosmological shadows finally brings the actual mechanics of our universe into focus.